Rob comes to us from Stanford University, and I've known Rob for probably 18 years now, and it's just absolutely impressive. And he's a man that I admire a lot. Just a little bit about his background. He's the Douglas Provostial Professor at Stanford School of Earth Science, but he's only been there for a few months now. He recently moved there from Duke University. And he's got an interesting academic background. He's like a lot of us, where we don't end up on the original path that we started on. He got his undergraduate degree in chemical engineering from Rice University. And after working as a chemical engineer for a few years, he realized that the real fun in life is had by ecologists. And so, so he walked into sort of the leading plant physiological ecologist in the West's office one day, and he said, I haven't taken a biology class since high school, but I think I want a PhD in what you do. And Martin Caldwell at Utah State welcomed him into the lab, and they did amazing work together at Utah State. He then went to Stanford for a postdoc. The University of Texas was his first faculty stop. And then he's been at Duke, and he's done really important work linking science to policy as well. He was he co-chaired the U.S. carbon cycle plan as they sort of established priorities for what we needed to do with regard to carbon cycling. He directed the Department of Energy's National Institute for Climate Change Research for the southeastern U.S. And while he's done all this amazing professional things, I think probably the thing that most impresses me is that he also has written books for the general public on environmental issues, and even more impressive is he writes children's poetry. And so with that, Rob Jackson. But do you need the mic on?
You need the mic on? Can you guys hear me in back if we leave the mic aside? If you guys can't hear me in back, you're not going to say anything. Yeah? Okay, if I start to sort of taper off or mumble or something, just put your hand up in the air and I'll put the mic on, which we can do if we need to, but let's try it without. Well, so first of all, it's a pleasure to be here. Thank you, Rick. One correction, I actually never had a biology class in high school or in college. So I had a lot of catching up to do when I went back to grad school. But I started taking night classes when I worked for the Dow Chemical Company, which was my first job out of college. And I had a boss who was very supportive and understanding. So I took some classes at night, would take very early morning classes, and then the rest of the day would do my normal job. So that was my circuitous career path, and I suspect many other people in the room have had a few turns in their career as well. It's a pleasure to be here because, as Rick mentioned, I did my graduate work in Logan at Utah State. Spent 5 great years here doing research, but also getting to fish and hike and ski and a few other things we like to do. And today I want to talk about hydraulic fracturing. So there's even though I was in graduate school, I trained as an ecologist, environmental scientist, and in statistics, there's not as much life sciences in this talk as I would like, because there's been very, very little work done on sort of organisms associated with hydraulic fracturing. So what we're going to do today is talk more about sort of water and air issues, and kind of talk about that, which has been what little work has been done, has been done the most. So what are people concerned about? What perhaps should we be concerned about and not concerned about, maybe in some cases, and why? And how do we know? How much confidence should we have? Let me cut the lights. Yes. There are some seats in there if you want to spread out. Is that all right? All right, here's a picture I took from a helicopter. So you're in Pennsylvania. You're in the Marcellus Formation. You're looking down on this operation. This is in the middle of the frac that's occurring. This is temporary. Doesn't last all that long. But you see the generators, the water, the mixers where the chemicals and the water and such are being mixed. And then in that back left corner, you see a house. Okay? So imagine how your view of this operation might differ depending on your economic interest in that operation. So you may own the mineral rights that that well pad is exploiting. Maybe your neighbor owns the mineral rights for that well pad. And they put the well pad on the border to your property to keep it as far away from your neighbor's house as possible. Right? And the setbacks at the time this photo were taken were only a couple of 100 feet from well pad to house. Or, equally commonly, maybe more commonly, in many states around the country, in much of the US, are severed mineral rights, which means you own the surface rights, but somebody else owns what's underground. And in many cases, people don't even know that they don't own their mineral rights. So this is one of the reasons I believe why this process is so controversial, because you have this industrial activity in people's backyards, replicated thousands and thousands of times in different places, different conditions, different people of social and economic backgrounds, and different literal interest in that operation. So, just to illustrate the proximity of where people live and the operation, even in relatively rural areas like northeastern Pennsylvania here. So a few minutes of background, and I'll insult some of your intelligence because I know you know a lot about these issues, but just bear with me for a few slides. We'll go through. Here's a global map of where the shale and oil is around the world. So essentially all the extraction that has occurred to date has occurred in Canada and in the United States. These are different plays. There's a lot of these resources in South America. Argentina has already drilled a couple hundred exploratory wells. They know how to get oil and gas. Across Russia, Northern Africa, across Europe, Australia. China has enormous resources. China has been slow to develop its natural gas, even its conventional natural gas, but they are speeding up very rapidly. And this map doesn't even include the tight sandstone, the other tight formations that are prevalent in areas of the western U.S. and many other areas around the world. So the point is there is a lot of this. Just because you have color on this map doesn't mean the resource is of the same quality. And there are many other conditions that go into whether you can get that out of the ground economically. But this is here to stay. And how we go about safeguarding the extraction that happens in different places around the world is important. And there may be a handful of you who in the room only who don't know how this works or haven't seen this. So again, indulge me for a few minutes, and we'll move on to some science. But here's just a schematic. There's a well pad, the drilling rig in place, temporary also. Two things have to happen to go down and out. So the two steps are a horizontal leg. So first, the company will come in and do 3D seismic imaging. They'll track where the shale formation is underground. In the U.S., on average, it's somewhere between 1 and 3 miles under the ground. Think of it kind of like the layer of icing in the center of a cake, only it's not perfectly flat. So it's tracing up and down like this, and through the 3D seismic imaging, real-time drilling technologies, they can track that formation that in many cases is only 50 or 100 feet thick. So they're going down. Going out, the out part, the horizontal leg, is getting increasingly longer. So each individual well is becoming more intensive. And then once that horizontal leg is in place, then the literal step of hydraulic fracturing occurs, where the companies pump millions of gallons of water and chemicals and other things and sand to prop open the cracks underground at high pressures, to crack open that rock, to open up the rock to allow the oil and gas to flow back to the oil well and up to the surface. Neither horizontal drilling nor hydraulic fracturing is new. As most of you know, hydraulic fracturing goes back at least to the 40s, and even before that, people were throwing dynamite and nitroglycerin down wells to sort of break up the rocks underground. Then the horizontal drilling goes back at least to the 80s, but the combination of the two, the lengths, the intense pressures that are used, the high volumes that are used, is somewhat new. So there's true in both statements that it's old and that there are aspects of it that are pretty new. What are people worried about? Well, this is a partial list. Here we've got land disturbance, so you have road building, you have the well pads themselves, you have pipelines that are built. You have all sorts of things that affect the land surface. You have the water requirements. The literal water used to hydraulically fracture or frack the well. We'll talk about that today. Drinking water quality is something that we've worked on. Our groups at Duke studied, or did the first studies looking at relationships between drinking water quality and proximity to these shale gas wells. We asked a simple question: is your water any different if you're living far away from a well or if you're living close to the well? And if it's different, why and in what way? The disposal of produced water is another, perhaps even the biggest issue associated with water. In these oil and gas operations, we generate almost 1 trillion gallons of wastewater a year from all oil and gas operations in the United States. We've got to do something with that wastewater. Pump it underground, back underground for the most part, treat it in some cases, recycle it in others. Every state does it differently. Air quality interactions, and then we'll talk about air quality a bit today, and then induced seismicity is particularly important in the UK because when they did some of their very, very first exploratory wells, they had some induced small earthquakes induced from that operation. You're hearing about this, some of you I would wager, particularly in Oklahoma, where there have been a whole series of earthquakes over the last decade, and over the last couple of years at least, Oklahoma has had more seismic activity than where I live in California. And so that's different, and that's primarily associated not with the hydraulic fracturing itself, but with the wastewater disposal. So anytime you pump any fluid, whether it's carbon dioxide or water or anything else underground, high pressure and high volumes, you can cause rock faces to slip along faults and such. So you're essentially lubricating those faults. And that's what's been happening to Oklahoma, but associated with other processes too, in addition to hydraulic fracturing. So what we're going to talk about today, and the things that I work on, and our group works on, are the water side, the air side, and then just in the interest of time, we won't cover wastewater. It's really, really important. What are some good things that are happening on the waterfront? Well, in states like Pennsylvania, at least, companies are now recycling about 90% of the wastewater that they receive. It comes back up out of the well through time. We call it produced water. And they're using that to then hydraulically fracture the next well, or at least part of the water used. That's good because it reduces the amount of fresh water you need, and you're taking from somewhere on the surface or from groundwater, and it reduces the amount of wastewater that you have to get rid of. Now, wastewater's nasty in areas like the Marcellus. It's much saltier than seawater, contains naturally occurring radioactive materials, it can be high in elements like arsenic and selenium that are health concerns. So that's a really, really good development. Not done in states like Texas, California, North Dakota, because there's abundant wastewater deep injection wells, class 2 injection wells in those states. So the cheapest option is to stuff it back underground. All right. Greater disclosure of chemicals in different states have passed enhanced disclosure laws. The devil in the details here is what the trade exemption clauses are in those. But there's more information available now, not as much information as we would have in a perfect world, and that transparency is important because the more information we have, in my opinion, the more likely it is that we'll phase out the more toxic chemicals, and the companies will get credit when they phase out those more toxic chemicals from their operations. All right, some companies have suggested they can frack without chemicals at all, not likely to happen anytime soon, and then green completions and elimination of open wastewater pits is another thing we'll talk about a little bit. Let's start with water quantity, then we'll go to quality, and then we'll do air. And then we'll be done. So the view of water use, not surprisingly, is really scale dependent. So first let's take a really big macro view. Let's talk about the US. And let's talk about it at a state level, like Texas in this case. Now, if you look at the water required, or the water used currently for hydraulic fracturing, it's really quite small. It's about 1%, or even slightly less than 1% of all the water that's used in the state. So you have municipal uses, you have the biggest uses being agriculture, clearly, and then you have water used for power plants. So power plants, and especially agriculture, are the two ways that we use most of the water in this country. But then you start getting a little smaller scale. You go down to the county scale, in towns and such, and then it's a different picture. So in a dry state, this is a picture from the Eagle Ford in Texas. On the right is the Marcellus in Pennsylvania, another photo I took from a helicopter. There's an open wastewater pit there that you see next to the well pad. Now all of a sudden, in a dry state, where you have groundwater pumping, you can have 10, even 40% of the groundwater that's pumped in that county go into a new application of hydraulic fracturing. Now all of a sudden that's a meaningful amount, right? And you have these complicated situations where in many of these areas the aquifers are dropping, and some people say it's hydraulic fracturing, other people say it's a drought, and other people say it's because there are more people in the area, and you have to try and tease apart all those different possibilities, and in some cases all of those possibilities are correct. And so at the smaller scale though, these water requirements can be very intensive, and especially in the drier areas. So it's not surprisingly the western half of the state that this is of the country, that this is particularly concerning. In a wetter area like Pennsylvania, it's mostly about not allowing too much water to be taken from any particular area. So they had problems with this early on in the Marcellus. The Department of Environmental Protection recognized that and then fixed those and changed the rules for those. And so very scale dependent. Let's do a few comparisons. I just have a little bit of data that I'll show you. Here's a recent analysis we did to quantify the amount of water that goes into hydraulically fracture a well. So what you're looking at here is 7 or 8 plays around the country, North Dakota, Texas, Oklahoma, Arkansas, different areas. This column is the amount of frac water used per well, liters on top, gallons in the bottom. So on average, about 4 million gallons is used to hydraulically fracture a well. However, that's not the end of the story. If you're interested in comparing different energy technologies, you've got to know something about how much energy you get back up. Because if you use more water but get more energy back up, it may or may not be more water intensive than some other things that we use, including even conventional natural gas. Right, so that's what you're looking at here. These are the estimated ultimate returns for these wells. Now these numbers are pretty well known. These numbers are a little fuzzier because in these numbers you have to make some assumptions about how long the well is going to produce, how many years, and you have to make some assumptions about what the decline curve will be for that well. So if prices stay really low, for instance, perhaps the well doesn't produce for the 30 to 60 years that it might otherwise. But anyway, with some good numbers here, we can then get a water intensity estimate of about, in this case, about 8 liters per gigajoule. A gigajoule of energy is about a sixth of a barrel of oil, say, just in kind of round numbers. All right, so it's a water-intensive process. It's not more water-intensive than some other things we do, though. You can compare unconventional oil and gas here. So here's our water intensity for unconventionals. It's a little more water intensive than conventional natural gas. That's not surprising. The conventional natural gas is easier to get out of the ground. You don't have to break open the rocks to get it to the surface. But then you look at something like pulverized coal. Things in the eastern half of the U.S. in some areas of Utah and such, coal is an important resource. It's more water intensive than hydraulic fracturing on an energy basis. About twice as water intensive, and that comes partly from the extraction, but in the case of coal, has more to do with dust control and processing than literally getting it out of the ground. Tar sands and oil shale is relatively water intensive. Biofuels is one of the most water-intensive technologies, corn ethanol in particular, because of all the water that's used by the corn plants. So that's a more complicated situation because you don't know what that water would have been used for otherwise. You don't know what the opportunity cost for that water is, but just on a literal sense, biofuels are water-intensive. But compared to renewables that use essentially no water, fracking's much more water-intensive. The one exception there on this list is concentrated solar power, which is used big arrays in the deserts, and that's water intensive because of the dust control that's done. But anyway, compared to these other fuels, the story's a little more nuanced. Less water intensive than some other fuels we're used to, like nuclear and coal. More water intensive than wind, solar PVs. Okay, how about water quality? So where might water interactions occur? What might we look for, and what can we do about it? Here's just a cartoon, if you will, of a well pad. Here's the drilling rig here. So you see a number of ways on this slide where you could get some interactions. Here's a river, but it could be a lake, it could be a stream, a pond. So you might have a spill from this site to here, hypothetically. You might have water that's used from here to fracture a well here. You might have an open wastewater pit, like I showed you in that one picture from above that you were looking down on. Those pits are lined in most cases, but not always. Sometimes those liners get ripped and leak. Sometimes those pits can have organic, volatile organic carbon compounds in them, or compounds in them that can volatilize into the air and might drift downwind. So if you're living close to one of these operations, you might be exposed to different things in your air than you would otherwise. You can have spills here, and then something that I'll talk about next is actually what's happening here in sort of the top, if you will, few hundred feet to 500 feet. So most people, when they think about water issues, I believe, they're worrying about what's happening down here. So the hydraulic fracture might be 1 mile to 2 miles to 3 miles underground. So it's a long way from any of the stuff going on up here. But water contamination can also happen if a well leaks. If the cementing is poorly done, if the casing leaks here, these are some interactions that we'll talk about now. So, and the take-home message for this part of the talk is to not ignore what's happening down here, but in terms of environmental stewardship, to pay more attention to what's going on up here, including these top few hundred feet underground. Because that's really where, in my opinion, most of the action is. Let me talk about some of our studies. In this case, the Marcellus. These were the first papers that looked at drinking water interactions. You're in northeastern Pennsylvania here. Here's New York. Each of these triangles and squares there are individual homes where we went into the homes, went into their wells. All these people are on private well water. These are rural areas. So they don't have the protections that people using municipal water have. All right. This is an interesting comparison for us because, as you know, New York has had a temporary moratorium on high-volume hydraulic fracturing. So this is like a fence line comparison for us, where we can get very similar geology, but not have the high-volume hydraulic fracturing occurring just across the border there. And as you all heard in the news a week or two ago, New York just sort of codified that ban, at least for the Cuomo administration. All right, and these red ones are wastewater samples we've obtained, and the map is much more extensive than what you're seeing here. All right, so we identify homeowners, we go to their house, we take their samples, take samples of their water and analyze them for salts, for metals, for radioactivity, for dissolved gases, and other things. And answer that question, is your water any different if you're living near oil and gas wells or farther away from it? The short answer to that question, for most things, so far in our work at least, is no. Right? So we don't see evidence for radioactivity getting into people's water. We don't see evidence for changes in salts or metals. We haven't had, throughout this research over the last 5 years or so, we haven't always had the capability to do the organic compounds, the BTEX, benzene, toluene, xylene compounds that people are concerned about, although we are doing that now. And don't, in the cases we've looked so far, don't see evidence for increases in those. What we have seen some evidence for so far, in a minority of cases, is stray gas migration, or stray gas contamination. So what you're looking at here is distance to gas well. So here's the well, here's far away from the well in kilometers. So you're out about 3 or 4 miles here. The y-axis is the concentration of methane, dissolved methane in the water. The gray band is the band set by the Department of Interior. That's where they suggest taking action to reduce the amount of methane in your water. And anything above that gray band is saturated in methane and bubbles like champagne. Right, so what you see here, first of all, is that most of these people have detectable methane in their water and gases that's naturally occurring. This is just the legacy of living over an area that has oil and gas and hydrocarbons in the source rocks underground, and that material migrates upwards over thousands and millions of years. So most of these people have detectable gases in their water. However, if you're within about 1 kilometer from our work, you're more likely to have these very high concentrations of dissolved methane in this case. And statistically, much higher probability. And when you look at the heavier gases like ethane, it's even clearer, because then you don't have really any of the noise out here, and you have these higher concentrations only in a narrower band. That's useful to us because for methane, you got all sorts of sources in the environment, right? So you have wetlands, You have microbes in the aquifers. You have biological activity as well as the thermogenic, the fossil fuel methane and ethane. But microbes don't give off ethane and propane in these environments. Right, so if you're living within a kilometer, in a minority of cases, there are still more people down here, even within 1 kilometer, than there are up here. All right, where might that gas be coming from? That was work I'll try and credit some of my co-authors as I go along. That was Stephen Osborne, who was a postdoc, and much of this work was with my close colleague Abner Vengosh at Duke. Here now you're looking at, instead of well, let's stick with distance to gas wells. Here's the ratio of helium to methane. Now, noble gases have become really useful to us because noble gases don't react, as you all remember from your chemistry class. So they don't react. They're not fractionated by biological processes. They are fractionated just by a handful of simple physical processes in the environment. So they're sort of parallel tracers, if you will, that are also found down in these formations. So here's a ratio of helium-4 to methane. Helium-4 is formed radiogenically. It's formed by decay of uranium, for instance. Here's our array across the landscape, across the distance. You see about an order of magnitude almost variation in this. The colored dots are the concentrations of methane, dark being higher concentrations. Here's a natural salt spring. This is a place that occurs naturally where water and gases bubble up to the surface. Almost surely because of a fault that's associated with it nearby. All right, so you see this spread, but then within a kilometer again, you start to see some other things. If you compare the helium and the methane in the source gases, so upper Devonian is not all the way down at the Marcellus, but is layers of gases that are found in between. These are layers that were drilled previously, nearer to the surface in more conventional ways in some of these areas. And then here, of course, is the Marcellus. That's about a mile or 2 underground. So we see some homes where the gases in their water look like these intermediate pools, and we see other homes where the gas in their water looks exactly like the Marcellus. And we'll talk about why we believe that happens, but we believe that's attributable to cementing issues here and casing issues here, and I'll talk about that more in a minute. We'll finish this part with one more example. Now let's take again, a more nuanced view of what happens, or what occurs naturally. So there are stories in this area of people whose grandparents can light their water on fire because of the methane in the water. And those stories are true. Right? So you have people across this area, you have different quality of water, not surprisingly. You have people with very pure water. This is chloride down here now, just one salt. Here, methane to argon, 36 in this case. So you got really super pure quality water here. You got pretty lousy quality water here. These people up here are the people who can light their water on fire, naturally. But the point is that methane, high methane in that water comes with other things. It tends to come in water that's generally poor quality overall. And also important for our purposes, there's no difference between the circles and the triangles here statistically. That means in this case, it does not matter whether you're living far away or near to one of these oil and gas wells, and it shouldn't matter because the companies don't sniff for methane where they put their well pads down on the ground. It's not like the Beverly Hillbillies, for those of you old enough to remember the Beverly Hillbillies, like me. Right? So they're covering the landscape in a checkerboard fashion. So there's no difference between them. There's this pretty good relationship between salts and other things and the concentrations of gases, and then there are the anomalies. Then there are the people who have very pure water here, and they've got gas in their water like that. But that's not normal. And we've sampled long enough now. Many of these cases are not cases where we have pre-drilling and post-drilling data. That's what you'd want to have in every case. In most cases, you can't get that. But we have it in enough cases now to see people go from here to here through our sampling time. Right, so what's happening? Why in a minority of cases do you get this stray gas contamination? And what I would argue is that the stray gas contamination is important because a well that leaks methane is a well that leaks. It's an indication that there's a problem with that well. So what are some of the possibilities? Well, you have some natural sources. Here's what people are worried about. Hydraulic fracturing, opening cracks that go all the way to the surface, or perhaps intersect a fault that runs to the surface. You have some abandoned wells, particularly important in some areas of the country, not so much in northeastern Pennsylvania. But if the hydraulic fracturing operation or the drilling operation intersects an abandoned well, then you can have a conduit, a pathway to the surface. So we, except in very special cases of abandoned wells that have been identified, we don't think that's what's happening. What we think is happening is mechanism 4 and mechanism 5. So mechanism 4 is that the cement is poorly done. So the cement is what protects the annulus between the rock wall and the casing. It's that donut, if you will, that's filled with cement to keep things from moving into, up, and out the well and into surface water. So let's say you have a gas-rich pocket here under pressure. If the cement isn't sealed properly, the gas can move up and out into the surface layer, and that's what we see. Okay, in some cases. Then, in the cases where they match the Marcellus, you can have a casing leak where the steel tubing actually might be cracked, the joints might not be sealed properly, and then you can have stuff leaking out here. It's an important distinction because in this case, you never expect to see hydraulic fracturing chemicals and such, because there isn't a connection to what's inside the well. But in the casing situation, there is. So let's move on and finish this quickly. One of the spirit of the work in our group is both basic understanding of the science, but also to make a positive difference. So in some of the recommendations that we made, for instance, with this 1 kilometer distance, was to enhance some of the safeguards around the well and to enhance the presumptive liability distance, the distance over which companies pay homeowners to have their water tested before drilling. So it protects the company from paying for problems they didn't cause. It protects the homeowner if their water goes bad after the drilling operation. So this is an example of the Pennsylvania's new law that was passed in 2012. Work led by Richard Davies in the UK, who tried to summarize well integrity data globally. Apples and oranges, onshore, offshore, old, new. But in general, for older fields, anywhere between 1% or a few percent to a few tens of percent of wells can have problem, at least pressure problems through time. Doesn't mean all those wells leak to the environment. So we need more information about this. And the legacy effects are sort of an extension about that. What happens sort of in a 25 to 50, even to 100-year time frame? So these are all wells. I took pictures of these wells in Pennsylvania that I took, about a month ago. There are conservatively probably 500,000 legacy wells in Pennsylvania that aren't plugged. Most of them aren't like this, but some of them are. And we know almost nothing about these wells. We don't even know where most of these wells are. All right, so the question here is, what can we do today? What should we be doing today so that we don't have issues in 25 and 50 years? All right, so some take-home messages. Hydraulic fracturing is water intensive, but not as water intensive as some other fuels. More water intensive than renewables, or most renewables. The focus on surface operations and the sort of well integrity, especially in the top sort of few hundred to 500 feet, is where I think the action lies. And then importantly, the good policies and best practices make a difference. Not all companies are the same. Not all geologic plays are the same. You don't see these kinds of interactions in Fayetteville in Arkansas, where the geology is also tighter. All right, let's finish with a few examples from the air side then. That's water. We've talked about quantity. We've talked about water quality. Now let's look at the air. What might be in the air if you're living downwind, if anything, in these operations? What about the greenhouse gas balance that's gotten so much attention over the last few years? How much methane leaks to the atmosphere as a more potent greenhouse gas than carbon dioxide? So there are, to continue the coal analogy, there are clear carbon dioxide benefits to switching from coal to natural gas. It's about half as CO2 intensive. But depending on the methane leakage, it could, if methane leakage were really bad, and it doesn't look like it is bad, it could offset those greenhouse gas benefits. So our group has been working both upstream at well pads, downstream at city streets. And I'll give you some examples of this kind of work now. So it's important to point out, just like in water, that there are some clear benefits for some energy transitions. So if you take an old coal plant offline and replace it with a natural gas, you reduce particulates and sulfur and mercury. These are things that kill people. Thousands of people a year still in the United States. Not as pure as wind, solar PV, but better than coal. So which fuel will it offset over the coming decades? air quality and health concerns for workers, people living nearby, compressor stations, ozone interactions, things like that. And then methane leakage, these are estimates from the EPA. About half of the leakage is estimated to come on upstream operations near the well pads and processing facilities. And interestingly, about half of it's estimated to come downstream in the pipelines. Right, so we'll explore those interactions a little bit. There's been a lot of work done in this area over the last 3 or 4 years. This is work by Dave Allen's group at the University of Texas. They got on well pads, scrambled around these well pads, and bagged and estimated actual leaks from valves and pneumatic controllers and tanks and things like that. And you can use this information to put into life cycle analyses and models, such as the EPA uses, to estimate what the total leakage should be. So you combine an emissions factor with an activity factor, so leaks per valve with numbers of valves across a play or a well pad or state. And that's what the EPA does, and some of the states do for their inventories. So Dave's numbers show very clearly that from the bottom-up estimates that the numbers are pretty consistent, maybe even a little lower than what the EPA suggests for the well pad themselves. And most importantly, that there's at least a 3-fold variation in the leakiness depending on the best practices that different companies use. So different companies, in some cases, are doing a better job than other companies. All right, so bottom-up estimates are consistent with the EPA. Top-down estimates aren't. So if you're not scrambling across a well pad, but you're up in an aircraft or a helicopter, or you're using a tall tower to sample the air in a field, many of these studies suggest that the estimates are higher than the EPA and the state inventories suggest. So here's an example from Colorado. This was really the first example of this case in the Front Range. The NOAA folks, this is Gabby Patron's work and others. So what they did, they have this tall tower in Boulder. They've been monitoring the air just for many years for background information, and they started noticing pollution plumes from 2 directions. From the south, not surprisingly, from the Denver metro area, but also from the northeast to the southwest. Across these purple dots are the oil and gas wells in that area. So they put some sensors in a car, and they started driving around that area to look at leaks. So they combined that surface work with their aircraft work and estimated that methane and VOC emissions, the volatile emissions, are 2 or 3 times as high as the inventory suggested they should be. And then benzene was almost 7 times too high. Benzene numbers are a little fuzzier, a little harder to do. But anyway, from the top down, the numbers look higher in some of these plays than people get by scrambling around the well pads. Well, why might that be? Well, first of all, when you're going from the top down, you have to separate out different sources, right? So there's methane in the air from cattle in the Front Range and wetlands and your landfills and all sorts of things. And when you're working from the bottom up, you have to have access to the well pads. So are you sure that the companies who are giving you access to their well pads are representative of the industry as a whole? And are you getting a random sample of locations, or are you sort of shunted to a particular area? But there's another explanation too, and that's I think an explanation that's gaining a lot of traction, and that's sort of high emitters or super emitters, to be dramatic about it. So in business, you might call this the 80-20 rule. But what if 0.5% or 1% or 5% of the operations in an area leak a whole bunch, and everything else leaks just a little bit? And that increasingly is what we're seeing evidence for. So here's an example. This is a tank from the Barnett, where we took an infrared camera image. Now these are invisible to the naked eye. So this is long wave radiation. This leak from that tank was equivalent to about 300 houses worth of natural gas for an average house across the US. That's probably human error. Probably a thief hatch or something that was left open after somebody sampled the gas that was in that tank. So how common? How prevalent is that, and how would we know? Well, one of the ways we've been trying to do it, and this is work with the Environmental Defense Fund, is to fly random areas of plays across the US. So we've now flown about 8,000 well pads and operations across 7 plays in many states in the US. And you use the infrared camera to give you a qualitative, it doesn't give you a number for the emission, but it gives you a qualitative sense of how prevalent these big leaks are. So here's just an example of a small well pad. You're looking at a couple of tanks. This is in the Eagle Ford Shale in Texas, an oil shale area. That's an invisible leak. And the interesting thing about this work is that what clay you're in makes a huge difference. So we see anything from about 0.5%, 1 in 200 wells like this, to in some places up to 5 or 10%. So if we can have detection mechanisms, low-cost detection mechanisms that allow us to identify these kinds of things quickly, the supermineral problem in a way is a good solution. It's easier to fix this than it is if every valve and every pneumatic device leaks the same amount, and you got to lower the emissions from all of them. So we'll finish, last example, downstream. We're almost done with leaks from cities. So our group, and this is collaborative work with Nathan Phillips at Boston University, we did the first publicly available maps of city leaks. So now you're looking at that methane leakage from distribution lines in streets. So you have the analyzer in the car. And the first city we did was Boston. We put that analyzer in the car, drove every block across an 800 road miles of Boston Metroplex. Okay, when we see a high concentration, we can hop out of the car and sample that leak. Here's the map for Boston, work that came out about 18 months ago. Red is road miles driven. Yellow are the leaks. About 3,400 leaks across the Boston Metroplex. Number one predictor of a leak, old cast iron piping. Some of it 100 years old. Okay, we can source well, first of all, in terms of responses, when that paper came out in early 2013, the mayor responded the next day. Then Congressman, now Senator Markey, responded July 2014. Massachusetts last summer just passed an accelerated pipeline replacement bill for the state to try and speed up the replacement of those old pipes. Are we sure those leaks are natural gas related? We are. Here's a last sort of data plot I'll show you. This is the isotopic signature, sort of thermogenic here, biological over here. This is the ratio of methane to ethane. Just like that's useful in groundwater, it's useful for us in air. And the biological sources, landfills, wetlands are way up here. The microbes don't give off methane, but the methane's in the pipeline of the city. So even in spite of all this noise down here, the red are the pipeline data. They cluster around these pipeline values. Okay, we're just finishing a rooftop analysis that provides the emission estimate for the whole city. And unfortunately, it's embargoed, won't be out for a couple of weeks. But in this metroplex, anyway, it's going to be higher than the state thinks it is. And we'll finish with DC. DC, this is a map we produced earlier this year. This is about 6,000 leaks in DC. Here's the Capitol building. Right here, there's Capitol Hill in back. Old infrastructure. The Washington Post has an app. You can plug your address in and look at the leaks near you based on our data. How might we use this? Well, let's say you take the top 50 or 100 leaks and use that to make recommendations to fix them. We're not in any way suggesting that a company should go out and fix 6,000 leaks. That's not cost effective. But we can use the information to prioritize the places to work, we believe. Safety is an issue. In DC, we have the top 20 leaks. We hopped out of the car, found where that gas was coming from. In 12 of those cases, the concentrations in the manholes were explosive, greater than 50,000 ppm. We called those in. We went back 4 months later, tested them again, and 9 of them were still explosive. Now, that shouldn't happen. Who's doing a good job? Well, some cities are. So here's a last graph, I believe, number of years to replace the rest of their cast iron piping for different cities. Cincinnati, Ohio, great example. The company, in this case Duke Energy, the Public Utility Commission, then the city and the state got together and 15 years ago or more decided they were going to work doggedly on replacing their old infrastructure. So they've been doing this for 15 years now. They're almost done. They were just a couple years away from having none of this old infrastructure left in their systems. Who's on the other end of the spectrum? Baltimore, Maryland. These are all data based on what these companies actually did over the past decade. All right, so you look at what the pipeline that Baltimore replaced over the last decade, they're on track to be finished in the year 2150, when all the rest of their pipes are 150 years old. And do these things make a difference? They do. We spent the last year mapping areas where these pipeline replacements have been put in place across cities, and you see orders of magnitude fewer leaks in those locations than you see in cities like Boston and DC. Anyway, so these are the reasons for fixing the leaks. Downstream, consumers, the ratepayers pay for the gas that goes missing. Job creation, safety, air quality, and climate change and greenhouse gas emissions. So I'll leave you then with, I guess, with that thoughts, and we have time for a few questions. Where will our energy come from? We have this abundant new source. What fuel will it offset? These are some photos of a mountaintop mine. I used to fly over these mountaintop mines when I went to work from North Carolina to the Marcellus, and that's a pretty intensive way to generate your energy too. That's a societal question. Thanks for your time. Any questions?
I have one. So the pipes that are leaking methane, are they carrying natural gas?
Yes, they are.
So earlier with the water contamination, have you sampled any areas of known wells that have not yet been drilled?
So the question, I should have repeated the other question. The question back was, have we sampled in areas where wells have not been drilled yet? And the answer is yes. So for instance, we have a paper in press now where we've just provided a baseline for North Carolina that has no history of oil and gas drilling. So we went in with the USGS and sampled wells there. And then we've sampled areas in places like the Marcellus before the drilling has occurred. So we're watching that through time. Is that a question or a stretch? That's a stretch.
If you're detecting these leaks with infrared thermometry, I mean, that's a pretty ubiquitous instrument. Why aren't the cities and utilities using that more?
Well, they do. Companies do. But first of all, those cameras are $75,000. But as in most things, it's not really the expense of the equipment. It's the people time. And you have to have someone out there, probably in a truck, driving. Let's say it's your job to check these well pads with an infrared camera. So imagine driving across that landscape, from well pad to well pad. That would be slow. Or flying, they do some. They contract those out, but it's a money issue.
What kind of health cases are involved with methane in the water?
So methane in water is not regulated by the EPA, so it's not known to have a direct health effect beyond the obvious flammability and such cases. So this is why that's a great question. This is why I tried to say, I think in cases of human health, the issue is that methane is an indicator of a well where there's a well integrity problem. That doesn't mean that there are other things in the water, and I think it's quite clear saying we have not seen evidence for those other things. There have been a number of studies looking at air quality on the air side, showing increased exposures in some areas for people living within about half a mile or so. But there have been almost literally no health studies, actual human health studies associated with this process, and that does not imply or suggest that there are big health effects. There's just, we don't have any information on it. Almost out of time.
What about biological communities? Any work being done on how microbial communities or sort of bottom-up effects are
Yeah.
tracking?
So the question was about biological communities. Great question for a life sciences college. So there's an increasing amount of sequencing that's being done. There's some work. So first of all, let's separate it into sort of tracing. There's some people trying to use the microbes that are found deep underground, and you can see if they occur or all of a sudden are found or detected in these shallow environments. But then there are also people starting a little bit to look at communities, some of the ecology, especially out west around road building, sort of land effects I kind of mentioned. So some, but there hasn't been that much work done, especially biological and ecological. What's been done mostly has been microbial.
All right. Thanks, Rob.
All right, thank you.